Okay, a 59-kilogram diver drops from a board 7.5 meters above the water's surface. Find the diver's speed just before striking the water. All right, let's go ahead and look at this problem as a conservation of energy problem. So we've got a situation before and a situation after. Okay, so before the diver drops, they're on top of the diving board. They're standing at the edge of the diving board. Okay, and this diving board just so happens to be about 7.5 meters above the water's surface. And we're to find the diver's speed just before striking the water. So this is our initial condition. And then we're going to look over here at our final condition. Okay? So here, diving board's still there. But now, the diver is just about to strike the water. Okay? So let's go ahead and look at the rest of the information we know. Well, we've got our picture for the initial and the final. Next thing we're going to do is write down our givens. Well, we know that the diver has a mass of 59 kilograms. And that mass is not going to change as they fall, so you can go ahead and write that down for their final condition as well. We know they're starting 7.5 meters above the water's surface. So I'm going to go ahead and say the water's surface is height 0, which means that the diver is at a height of 7.5 meters to start. And we know the diver is dropping from the board, so they're not going to jump off the edge, they're just going to drop off the edge, just going to walk over and drop. So the initial velocity here is going to be 0 meters per second to start. Okay, so let's look at the final conditions. Well, the final height is not going to be 7.5 meters because they're no longer above the water surface. They're entering the water, so 0 meters. The final velocity is what we are trying to find. We're trying to find the diver's speed. So we're finding the velocity, we just don't care which direction it's going. Okay? And this is the initial height. Okay, we're going to solve this problem using conservation of energy. So mechanical energy is conserved when there is no friction. In this case, we're going to ignore friction. We're going to ignore air resistance and just go ahead and solve. So we've got 3 types of mechanical energy. We've got elastic potential energy when an item is stretched or compressed. We've got gravitational potential energy, which is when the object is above or below the 0 level. And we've got kinetic energy when something is moving. So we're going to look at those for before and after. Their total, their sum, needs to be the same before and after. So I'm going to say the 3 energies. Before, the elastic potential energy plus the gravitational potential energy plus the kinetic energy before is the same total as after. Okay? Now let's look at each of these. Okay? In this situation, the before situation, elastic potential energy is when something is stretched or compressed. This is not a springboard, and they don't spring off of it. They're just dropping. They're walking to the end and dropping. So there is no elastic potential energy to start. So that's 0. Gravitational potential energy, that's when you are either above or below height is 0. Well, we're above, so there's definitely gravitational potential energy to start. Kinetic energy, well, the person is dropping. They're starting at a velocity of 0, so they're not moving. So the kinetic energy is going to be 0 to start. So on the left-hand side, all that I have left is gravitational potential energy. If we look at our equation sheet, we see that that is mass times the gravitational field constant times the height. And I'm going to say the initial height because this is the before side. After afterwards? Well, they're not going to be compressing the stretchiness of this water down here. Okay, so there's no spring being stretched or compressed, so there's no elastic potential energy. Gravitational potential energy, well, that's when you are either above or below the height is 0. We are at the height is 0. So there's not going to be any gravitational potential energy. Kinetic energy, that's when the item is moving. They're going to be moving as they enter the water, so there will be kinetic energy. Kinetic energy has the equation 1/2 the mass times the speed squared. And now I'm ready to go ahead and solve. Both of these terms have the mass in it, so I could divide right now by mass, and the mass would cancel out. But I'm going to go ahead and just substitute the mass in for the time being. So here I've got 59 kilograms times the gravitational field constant, 9.81 newtons per kilogram, times the initial height of 7.5 meters is equal to 1/2 the mass, 59 kilograms, times the final velocity squared. Go ahead over here, multiply these three together. We're going to get 4,340 and 93 hundredths. Half of 59 is 29.5 times the final velocity squared. I want to solve for the final velocity, so I'm going to divide both sides by 29.5. I'm going to end up with 147 and 15 hundredths is equal to the final velocity squared. Take the square root. Our final velocity is 12 and 13 hundredths meters per second. Now I keep saying velocity because I see the V there and it's just rolling off my tongue. But remember, without the hat on top of it, it is just speed, and the question asks for the speed. So this is the speed of the diver. Okay, if we want to know velocity, we could include a direction. We could say it's going down, so it's negative, but it's asking for the speed. Now, you might be asking yourself, couldn't we do this the way we did before when we had an object just being dropped from a height and use some of our equations for free fall? And the answer is yes. If you'd like, go ahead and do it that way. You should get the same exact answer.